Hi, welcome to Raw Math and my series of videos on exponential and linear problems, application problems. This problem says the deer population in Pennsylvania County between 2003 and 2007 has grown exponentially. The initial population was 10,000 deer, and 4 years later, there was 27,000 deer. Okay, so it says find a model for the number of deer in Pennsylvania County, and it doesn't tell us how to do this, so we could simply say we started at 10,000, A equals 27,000, and when we divide by 10,000, we get that A is equal to 2.7. The problem is it says how many deer will there be in 2020, and if I take 2020 and minus 2003, I get 17, and 4 doesn't go into 17. If it was 16, that would work fine. But because I need to be able to enter 17 years, I need this model to be yearly. So I need to go from 4 years down to 1 year. I need to take 2.7 to the 1/4 to find out that the yearly growth is 1.282 and that the population over time is 10,000 times 1.282 to the t. Now we can take this model and substitute in our 17 years. The population after 17 years is going to be 10,000 times 1.282 to the 17. Make sure that these numbers always match. Whatever's in the parentheses is what's in the problem on the right. And we do this calculation and we get that there's 682,490 deer in 2020. It says, is this reasonable? Probably not. But this is why models have a domain. The domain says this model is probably good from about maybe 2001 to 2009, maybe 2010. Beyond that, we're going to have to find a different model. Exponential would explode, and that's not how life works. There's going to be carrying capacities on the land, and there's going to be a maximum number of deer that can fit on the land. It says predict when the deer population is doubled. So we want to know when the 10,000 became 20,000. We want to know when 10,000 times 1.282 to the t becomes 20,000. When we divide by 10,000, we get 1.282 to the t equals 2. Here's the thing. If you're ever asked about doubling, tripling, half, you don't actually need your initial because you're asking when your multiplication rate will double the initial. And that time is the same regardless of if we started with 10,000 deer or 1 deer. It's the rate of change that'll cause it to double. Okay, to figure this out, I need to make t a real number, and the way I do that is I do the inverse of an exponential, which is a log. I take the log of this side and the log of this side. The beauty of log is it takes the exponent and brings it out front as a real number. T times log of 1.282 equals log of 2. Divide so that t is equal to log of 2 divided by log of 1.282. Make sure you close this parenthesis when you're using your calculator, otherwise the calculator will throw this into the parenthesis, you'll get the wrong answer. Anyways, the answer ends up being, it's 2.8. It'll double in 2.8 years. Now, we want to know when. We want to know a calendar year, and we can't write 2005.8. It doesn't make sense. So here is where it becomes really challenging. And my suggestion, unless you're otherwise told, is to do natural rounding because this is all guesstimation. There's no actual precision in a math model. It's just giving us broad strokes. So according to our model, it's in the 2005 year, so 2005 would be an applicable answer. But if we did rounding, it would be in 2006. And I usually go with natural math rounding because it hurts my head to figure out if it should be 2005, 2006, because there's so many factors that could cause it to go either way. So I round, then apply 2003 plus 3. So our model is from 2003. I added the 3 to get 2006. Okay. Now it says, predict when the population will be 45,000. So again, when will 10,000 times 1.282 to the t equal 45,000? Again, I'm going to divide by 10,000. So I have 1.282 to the t is equal to 4.5. Again, I'm going to take the log of both sides so that I have t times log of 1.282 equals log of 4.5. So that t is equal to log of 4.5 divided by log of 1.282. And when I do this calculation this time, I get that t is equal to 6. It's a much nicer calculation. So 2003 plus 6 is 2009. I hope you've enjoyed the video. Please subscribe to my YouTube channel, like my Facebook page, and I will see you on the next video. Thanks!